All right, hopefully you've had a nice little break and are ready to go for the last two examples on Faraday's law. So nothing new here, just going through a few more examples. Now, in this particular question, we're dealing with an electrolytic cell. So have in the back of your head, that means it's a non-spontaneous cell where a power source is going to be required. In this situation, we're going to specifically be using a molten, ding, ding, ding. Remember that means heated to such a high temperature that the ionic compound, in this case sodium chloride, actually goes into a liquid. It melts, right? And the whole goal of going through this sodium chloride molten solution is that we can produce pure chlorine gas. All right, a little bit of a twist in this one. We want to know what period of time. Notice the question is very specific to hours, so we're actually going to get an answer in seconds. We have to remember to convert it. Must the cell operate with a given current of 350 amps? And the whole purpose is to produce 10 kilograms. Again, be aware, there's that kilo. In actuality, we're going to have to convert that to grams in order to use it. Whew. So lots going on. Our beginning is to focus on not the redox reaction, because remember, a redox reaction already has the electrons gained and lost completely balanced out. We need the electrons to be in the half reaction. Otherwise, we can't actually use it stoichiometrically. So the half reaction that we're focused on is the one where chlorine gas is produced. And for chlorine gas to be produced, it's at the anode. So it's when two chloride ions, not aqueous, liquid. Remember, this is a molten solution. When those two chloride liquid ions produce chlorine gas and two electrons. There it is. There is our half reaction that is going to produce that chlorine gas. Now, there's a number of different things that we know about this. For example, we know the mass, and the mass is going to be that 10.0 kilograms. Similar type situation. We can go back to the data booklet, and this time we have kilo, which means it's 10 to the positive 3 as the prefix. You can replace that K with that 10 to the positive 3. So that means that we have a total of 10.0 times 10 to the 3 grams. Like I said, guys, literally, this replaces the K. All right, let's continue on with other information that you know. We have no problem with the molar mass of chlorine gas. Just be careful that you remember it's diatomic. So we have to take the molar mass from the periodic table, times it by 2. We're going to have 70.90 grams per mole. Where am I going with this? Well, guys, we have to be able to do a comparison. If we can figure out how many moles of chlorine gas that we have, then we're going to be able to take that and very nicely relate it to how many moles of electrons we have. Right? Stoichiometrically. This works out beautifully. Think about what other information there is. We already know the current. We already know Faraday's constant. So if we can manage to get the number of moles of electrons, we have everything we need to get the time. Okay, jumping back to the number of moles of chlorine gas. Formula-wise, the number of moles of chlorine gas is going to be equal to the mass times the molar mass, which means we have our 10.0 times 10 to the 3 grams times the molar mass, which is that 70.90 grams per mole. Look what happens here. Our grams cancel out, and oh, I just noticed I'm doing a messed up formula. See, this is why we write units, guys. If I didn't write the units, then I wouldn't have clued in that, no, actually, they don't cancel out because I read the formula wrong. All right, let's try that again. Number of moles is equal to mass over molar mass. We're going to have our 10.0 times 10 to the 3 grams divided by 70.90 grams per mole. Now this works. Grams cancel out. moles is going to be left over. And we have a total of number of moles of chlorine gas, 141.043. The number keeps going, of course, moles. All right, go back to the beginning. Our balanced reaction shows a 1:2 ratio of chlorine gas to electrons. That means that I can take this value and do a comparison. I'm going to divide by 1 and times by 2, right? 2-to-1 ratio. So we end up with a total number of moles of electrons then, once I times that by 2, of 282.087. Number keeps on going, of course, moles of electrons. All right, consider the information that was also given to us. Current. Current was listed as 350 amps, which is coulombs per second. Faraday constant, of course we have. And the whole point of the question is to find T. Now, very, very similar to what we did before. Difference here being is that we're going to have to take that Faraday's law formula of number of mole electrons equals current times the time divided by Faraday's constant, and we're going to have to isolate the time, get it by itself. How do we do that? Well, we can times by F on both sides. These ones will cancel out. Then we're going to have to divide out by I. I will cancel out. There we have it. I'll write it out again. T is equal to Faraday's constant times the number of moles of electrons divided by current. There it is. All right, let's start plugging in what we know. Faraday's constant is equal to 9.65 times 10 to the 4 coulombs over moles of electrons. That value is going to be multiplied by the number of moles of electrons, which you figured out before. This guy right here. So we take that, 282.087 ... moles of electrons, divided by the given current, 350 coulombs per second. Look what cancels out here. Coulombs is gone, moles of electrons is gone. We're going to be left with seconds. Perfect. It's exactly what we need. I'm not going to round it yet. Time is equal to, this is a big number, 77,775.53, keeps on going, seconds, guys. Okay, this is ridiculous. Way too big of a number. To convert that to hours, we need to use the ratio. So times the ratio of 1 hour having 3,600 seconds. Notice how the units cancel out. Seconds over seconds. I'll be left with hours, which is exactly what the question wants. Now we can go to our 3 sig digs, 21.6 hours. And there it is. The answer has now been found. Period of time in hours. There it is. All right, guys. So really, very, very similar question to what we did with the previous podcast, except the goal of this question wasn't the number of moles of electrons. The goal of this question was to still use a half reaction in a stoichiometric way, but then to find the moles of electrons and manipulate Faraday's law to get the time. A little bit of a switch. Okay. One more question, which involves one of our applications of electrolysis. What do you know? Electroplating. Remember what electroplating was? It is the utilization of electrolysis in order to coat another metal, usually a metal alloy like steel, in a pure metal. So, for example, plating silver onto something like, in this case, a lovely teapot or coffee pot. We talked about doing this with stuff like silverware, or kind of like something like this, Moscow Mule cups being coated in pure copper. Love those cups. So cool. Anyway, should be an arrow here. Now, first with this question, just to take note of what's happening, we're taking a metal ion and we're reducing it, and reducing specifically means, remember, you're gaining electrons, right? So reducing that positive metal ion, and that's just represented by M. M just saying some metal, and X meaning some charge, right? It's going to be a cation, and then we're going to add that specific number of electrons to it in order to get the pure metal, right? Now, the two examples that I gave you here, in this one on the left was silver. The silver represents the M, and the positive 1 is the X plus. Then, of course, we're adding 1 electron in order to get our silver solid, right? The opposite example on the other side here, we're taking copper ion. And with the copper ion, it has a charge of positive 2. So we're going to add 2 electrons. That's the X in this case. What do we get as a result? Our copper solid. So once again, all the M's and the X's that are right here are just saying, hey, this works for any metal cation. And the charge on that metal cation is going to relate to how many electrons it's going to gain in order to reduce to its metal pure element. All right, let's go into the question. Here we go. Think about that copper with the Moscow mules. Calculate the current. So again, a little twist. We're looking for I here. What current is required to produce 1.4 grams of copper solid, and it's producing it from solution in specifically 20 minutes. Well, it is still going to be stoichiometry. So what's our first step? We need a half reaction. Remember the scenario. We're trying to produce copper solid. That means that we have to have copper solid as our end goal. How do we do that? Well, we take copper ions, copper 2 plus, aqueous, add the 2 electrons in order to get the copper solid. Where do the copper ions come from? The copper 2 sulfate. Notice how this relates to what I was showing you before with the Mx plus an X number of electrons to produce the metal solid, right? Copper is the M, the 2 plus is the charge. I add 2 electrons to get to that copper solid. Okay, consider some of the stuff that we have here. I don't have enough information yet at all to actually have the exact current that's there. How am I going to get to that? Okay, think about Faraday's law. Oh, I don't want that to be red. Let's go blue. The amount of moles of electrons is equal to the current times the time divided by Faraday's constant. My goal in my question is to get this. Now, I already have my time. I already have Faraday's constant, but this is an issue. I don't have the number of moles of electrons yet. However, I do have a half reaction, and I know from that half reaction that the mass of copper is going to be 1.40 grams. Knowing that I have a balanced half reaction, this is super doable. Consider the molar mass of copper from the periodic table is 63.55 grams per mole. Knowing that, I can then get the number of moles of copper. Mass over molar mass equals 1.40 grams divided by 63.55 grams per mole. Our grams cancels out. We're going to be left with moles. Don't round this yet. 0.022029 ... moles of copper. Balanced half reaction. So I can take that moles of copper and relate it to my moles of electrons. How do I do that? By comparing the molar ratio, a 1-to-2 ratio. That means that I can take this thing, divide it by 1, times it by 2, and I have, my number of moles of my electrons. So when I take that and I times it by 2, 0.02 0.04405 moles of electrons. Okay, remember back, we've been given the time. It tells us in the question that this is on for 20.0 minutes. Now, minutes isn't good enough, guys, because Faraday's law requires seconds. So I'm going to have to use my ratio to convert that. There are 60 seconds in 1 minute. My minutes will cancel out. I'll be left with seconds. We're left with a total then of 1,200 seconds. We already have Faraday's constant. We're good to go, guys. We can now find back over here what our current is. This needs to be rearranged, of course, to get I by itself. So times by Faraday's constant on both sides, divide out by T. What we do to one side, we do to the other. T's gone. I'll rewrite this so it's easy to see. Current is going to be equal to Faraday's constant times the number of moles of electrons divided by the time. Start to plug stuff in. 9.65 times 10 to the 4 coulombs per mole of electron times the moles of electrons. We already figured this out. When you're timesing by the moles of electrons, that's what we got right here, right? That's what we used, that balanced half reaction to get. Okay, so that number is going to get plugged in then over here. 0.0440 long number, moles of electrons. All of that divided by the time in seconds, of course, 1,200 seconds. Okay, our moles of electrons cancel out. And we then, look what's left. Coulombs are left. Seconds are left. Ah, that's good. Coulombs per second is amps, is our current. 3 sig digs, 3.54 coulombs per second, or of course you could write this as 3.54 amps. And we are good to go. Question complete. Alrighty, guys, there we go. You should be all set to go through some questions involving Faraday's law. You can now complete all the rest of your assignment, which includes going back to number 2 and doing E, and of course finishing 3 in its entirety, 3AB, and number 4. Any questions? Email me, let me know. We can set up a phone call. We can set up a video call, whatever works best for you. Talk to you soon. Hope all is well.